You know, you can push as hard as you want against a solid brick wall. You can sweat, strain, absolutely exhaust yourself. But if nothing actually moves, well, physics says you've done zero work. Let's dive into what that actually means. Today, we're unpacking this step by step. We'll look at everyday effort versus physics reality, the actual formula for work, the work-energy theorem, conservative forces, and finally, power.
All right, let's jump straight into part one, redefining effort.
In physics, work is all about energy transfer. It's the result of a force literally moving an object. It's not about mental effort or how tired your muscles get. You can study all night or push that solid wall all day, but true physical work, it strictly requires a force causing an actual displacement. And here's where it gets wild. Work only happens when force and motion are aligned. Pushing that static wall, zero displacement means zero work. But get this, carrying a heavy bag perfectly horizontally, that's also zero physical work. Why? Because your lifting force is pointing straight up, but your motion is completely horizontal. They are perpendicular, so physics says no work is being done.
So how do we calculate this? Let's look at section 2, the math behind the motion.
Here is the formula. Work equals force times displacement times the cosine of theta. That angle, theta, is absolutely crucial. It's the angle between your push and the direction the object is actually moving. Are you helping the motion or are you fighting it? The angle decides. Oh, and we measure this entire energy transfer in joules.
Take a skidding cyclist, for instance. If they slam on the brakes in skid, say 10 meters, the road is applying a friction force perfectly opposite to their motion. Because they're completely opposed, the angle is exactly 180 degrees, which gives us negative work. It's literally draining the bicycle's energy to bring it to a stop.
But hey, forces aren't always perfectly constant in the real world, right? If a force varies, we can still find the total work. You just look at a force displacement graph and calculate the area under the curve. We are essentially just stacking up all those tiny little rectangles of work.
Now, you might be wondering, if we put all this effort into moving something, where exactly does that energy go? How does the universe balance the books? That brings us to section 3, the work-energy theorem. Let's talk about kinetic energy. It's basically a measure of the work an object can do simply because it's moving. The math is half its mass times its velocity squared. And since it's a scalar quantity, it only cares about how fast that mass is moving, regardless of the direction it's going. And this links perfectly to the work-energy theorem. It's beautifully elegant. It essentially tells us that work is just the transfer of energy. You put work into a system, its kinetic energy goes up. Take work out, and kinetic energy drops. They're directly linked. To put that into perspective, think about a 2,000-kilogram car cruising at 25 meters per second. That is over 600,000 joules of kinetic energy. Compare that to a falling raindrop, which holds just a tiny, tiny fraction of a single joule. Mass and speed scale up that energy dramatically.
Moving on to section 4, potential and conservative forces.
Okay, so unlike friction, which just permanently bleeds energy away as heat, we have these things called conservative forces. Think gravity or a compressed spring. They don't care at all about the wacky path you took to get somewhere. They only care about your starting and ending points. If you do a full loop and end exactly where you started, the net work done by that force is exactly zero. It's a brilliant illustration of how nature recycles. As long as only conservative forces are acting on an object, the total mechanical energy stays totally constant. Imagine a falling ball. It's smoothly converting its stored potential energy directly into kinetic energy as it drops, keeping the overall energy balance perfectly stable.
Finally, section 5, power, the rate of work.
Here is where time actually becomes a factor. Power equals work divided by time. So you might have the total energy required to climb 4 flights of stairs, but your power completely depends on whether you sprint up them in 10 seconds or take a casual 5-minute stroll. We measured this rate in watts, which is just 1 joule per second. So the big takeaway here is that force, displacement, energy, and time are all part of the same puzzle. They aren't just isolated textbook ideas. They are intricately connected through a few beautiful, rigorous rules that dictate exactly how everything in our physical universe moves and changes. I'll leave you with this thought. Remember our friend pushing the brick wall from the very beginning? Same push, same effort. But until that wall moves, zero work is being done. In physics, effort without motion is just exhaustion. True work is about creating actual change. So, what changes are your forces creating today?